All right, so this one is your part 4 video on chapter 7. So far you have learned about how to design by the case of dimensions being given, right? Or dimensions that you find, right? You can find the dimensions using your table 9311 in ACI 318. So you come out with your dimensions. And then once you come out with your dimensions, you select an amount of steel, you check that it satisfies minimum, satisfies maximum, right? You need to make sure that it fits within the width of your beam. And then you check your design strength just to make sure that it has the capacity, right? Okay, so this example 732 is still a part A, procedure A, right? Procedure A example, because the dimensions are given. So this is kind of a review of what you've been doing so far. The purpose for this is this triangular load. Some of you already figured this out, but because that was an example that we did before in homework, right? But here, this is your lowercase WU given 347 kips per foot right here at the top. All right. Oh, so I cut an error here. So 347, yeah. So this one needs to be corrected. So 347. Okay. So that's what we have, no, to match this number. All right. So 347, your F prime C, that is your 28-day specified compressive strength, is 4,000. Your yield value for your steel is 60 KSI. You're using number 3 stirrups, right? And of course, you're going to come up with your reinforcement and then sketch your cross section. So the purpose of this one was to show you how to deal with the triangular load, because in your table, you will find that it's given as WU L over 6, but the WU is a capital case W, not a lowercase w. And also, you look at this, the units will not match, right? Because you say, oh, that one is this one, and you multiply by the length, you only get kips. But your moment is supposed to be kips feet, right? Kips feet, that's what it is. So that one, then this doesn't make sense for this one to be the same as this one, okay? So what happens is that this uppercase WU is your total triangular load. That is WU multiplied by the length and divided by 2, because it's a triangular load, right? So half of WU height multiplied by base, right? And so that represents your total load. So your total load really is 1/2 of the WU. This is your lowercase WU times L. And so now your formula looks like this. And this will make sense. Now you get units of kips feet. All right, so we replace then the value WU, the length squared divided by 12, you get your moment, change it to kip inches, approximate your value of D. As I said, we can use 18, in this case 18 minus 2.5. And I'm clarifying here that this is B times H. I mean, normally that's how it's given, but just in case, I'm clarifying. Okay? So, this moment then has to be equal to your design strength. And your design strength is your phi factor, which is 0.9, your area of steel, we don't know, times Fy, right, times D minus A over 2. But the D minus A over 2 is replaced by 0.9 times your D value, right? And so from here you solve, you get 2.68, check minimums, is satisfy minimum. So we can use the 268, find your A value with that 268, and now that you have your A value, you will come in here and find the area of steel again by using D minus A over 2. Right? And so we solve that, 261, so there is not a big difference in this case. And we look at choices. There is a possibility for 6 number 6s. That give me 264, a width of 14. 3 number 9s with a width of 9.8, so both work. I'm going to try the 6 number 6s, assuming that I need to control that cracking. I want to very small cracks, so I want to put more bars in there to control that. Okay. So now, based on what I selected, right? Based on what I selected, we are going to find now the new value for A. So it will use the 264 here, the 60, the 0.85, your 4, your 20. Now I can find the real value for D sub T and D, one layer, and I do 18 minus the cover. Stirrup is only 3/8, number 3 bars, and then 1/2 of the number 6 bar, and that gives me 1575. Find my neutral axis, right? So it will be the actual A divided by your beta 1, and we will check C over D sub T. That will be 274 divided by 1575. That's 0.174. For grade 16, the limit is 0.375, and therefore we satisfy the requirement for A is maximum, right? What else? We also can pick up now the phi factor to be 0.9, and so if we have the 0.9, which is now here, so that's your 0.9. You also have the maximum, you for your yielding. So that means that everything is now working fine, and we can use the formula for moments, right? The formula for moments to find the actual design strength. So here is the formula for moments, right? So we do that. We replace the phi factor, which we already know, the 264, which is the area we're using, the Fy, which is 60 KSI, your actual D, your A value, and notice that we got 2079 versus 2060. Okay. So one thing that as you do your homework, right, you can guess at different areas, right? I mean, different dimensions. I can make my very big, so it will pass. Well, that's not the point. Mm-hmm. The point is that you maintain your design strength close to your required value. I would say maybe 20-25% is you want to go up and be conservative, okay? But usually, I mean, with it 10-15%, you're doing pretty good, okay? This is very close, so that's good. Okay? Doesn't leave you room for any changes, right? So that's another thing. I mean, if I know that in the future there's going to be changing load that'll be higher, then I will design for a little higher value, right? So those are the things that you have control over. So what is your final plot? 18 inches height, 20 inches wide, 6 number 6s that fit on the 20 inches because the 6 number 6s only require to have a value of 14 inches, right? So that's your 14 inches there. I did show you how to get that from previous examples. Just for showing you that here, let me do it again. So you design 8s, and we have the formulas that we're using are the one for spring 220. Okay, there it is. So we got that one, right? So we are using 6 number 6s. There it is, 6 number 6s, and the value is 14. And I don't need to put any corrections, right? Why? Because I'm using number 3, not number 4 stirrups. Okay? So 14 then is the width that I need. That's minimal width that I need. Okay? That's the minimal width, okay, in this case. All right, so now that I have that, we go back here and we're done. Okay, we have done our design, it is there. So the next thing comes is your procedure B. So before we do these examples in procedure B, of course, we need to learn what is procedure B. Okay, so let's go back here and learn about procedure B. Okay. Okay. So procedure B comes here, right? Now in procedure B, you do not have dimensions, right? Oh, so how am I going to do the weight of the beam if I don't have dimensions? I don't have dimensions, then I don't have weight of the beam, right? Okay. So then the first step is to assume a beam weight, okay? Now you're still learning, so I don't know really how to find a beam weight. Well, you still can use the table 9311 to just give you some dimensions, but the dimensions are only useful, this is important, they are only useful to find the weight. Those are not your dimensions for your design. Okay? That's just to have some kind of weight. Okay? That's important. You can use still the table like you're doing for procedure A, but those dimensions are not your design dimensions. Those are only to come up with a weight so you can start the process. No? Another way is, as you develop more experience, then you memorize something like this, right? And here, if my span length is 15, right? The approximate weight on a simply supported beam is 0.2. If it's a cantilever, it will be 0.7. It's a bigger beam, right? And so these are approximate values. These are in kips per foot. Approximate values. Okay. Right. These values actually you will not find them anywhere. I believe I was just dreaming one day and I saw, oh, that looked like a nice table, and I just put it in. All right. So those are approximate estimates of beam weights, but you need some kind of beam weight. Okay? All right. If you want to use for all your beams, let's say, oh, this goes from 0.7. A 10-foot beam, not very common. So maybe a 15-foot to 0.7. So that's about 0.85, right? So 0.42 an average. So I can use 0.4 for all my guesses. I can use that because it's a guess, right? So instead of memorizing this table, I can say, no, for simply supported beams, I'm going to assume 0.4 all the time. Okay? And that's good. That's an assumption. Okay? For the case of cantilever, you probably want to assume more like a 0.6 average, right? And that would be your guess. Remember, it's just a guess. Okay. All right. So find the required moment, right? Because now you got your weight of the beam, you got your loads, so you're going to find your corresponding value for your MU, right? And that's the first step. So that's the only reason you need the weight, is because without the weight you cannot find the MU value. So you need your MU value. So I need my MU value here, and that's why I need that weight. But as I said, you can replace this table with a 0.4, right? Right? And use 0.4 for all cases, or you can use here 0.6 for all cases. Okay? And that's good. Because later you're going to check that weight. Okay? So you have to start with something. All right. Now, what is the difference? The difference comes here, step 3. Okay? You are going to select your level of ductility. All right? And how you do that? That means you're going to select your value of epsilon t. That's what you're going to select, right? Remember that the minimum value that you can use according to the code is 0.003 plus epsilon ty, right? For grade 60, we know already that is equal to 0.005. That's only for grade 60, right? If you, for example, need to do redistribution of moments, right? Then the code says, oh, that epsilon has to be greater than 0.0075. You have to use that. Now, what is the redistribution of moments? Okay, let me try to explain that here. I have a fixed end beam, right? Right. So I have that. I put my load, right? I think I'm way too high. Okay, so you got your load in there, and my moment here, you know that already, that fixed end moments, right? Your load is WU, right? L squared divided by 12, right? That's the end moment. So those are both of the ends. How much is the moment in the middle? Okay, so remember. Okay, so you don't remember where you go? Where do you go? Your being formulas, right? So in case you haven't forgotten that, you go to your being formulas. Being formulas, there they are, right? Okay, so we're going to rotate and we're going to look for the fixed case, right? So there, no, right there, right? There is the case, right here. All right. So here is your case. Let me make it bigger so you can see it, right? And so now we have it here. There it is, very nice, right? This case, right? So we know that one, and then this one is WL squared over 24. That's what the value is in the center. Okay. So let me go here and do it blank. That would be better, I think. Okay. So we have our beam, we have our loads, and we found the moment here, WUL squared over 12 at the end, and right at the center, WUL squared over 24. One thing that you need to notice, and a long time ago, is that these, oops, that these, no, let's see what's going on here. Oh, I lost my point again. That if you do your bending diagram, right, it looks like this. Now, you do that. Notice that you add the WL squared over 12 that you got here, and the WL squared over 24 that you got here, right at the middle. That's always, okay? It's always going to be WU L squared over 8. Always. No matter what you do, there's always in the middle you're going to have that. Okay? The effect of the supports is simply to change the figure. So all you're doing is rotating the figure or shifting the figure up or down, but at the end, this part in the middle remains as WU L squared over 8, no matter what. Okay? You can do whatever you want. It's always going to be that. Okay. So why are we doing this? Well, so this beam develops that. So then comes the concept of plastic hinge. Now, you probably in analysis you'll learn about your hinge, right? Where the moment is 0. Well, that's different. That's an actual hinge where you cannot develop moments. A plastic hinge, you actually develop moments. Okay? But in order to do that, you have to design that beam to have enough ductility so it will deform enough to be able to develop that hinge and carry that moment. So it should be able to get to the larger value without failing. Okay? And that's what is called a plastic hinge. Okay? So everything is yielding in that location. Okay? That's all it means. So this one will get to this maximum. But notice that if your cross section has this capacity, then this one is not a full capacity, right? And so then this one starts sharing some of the load and is passing the load to this guy. So what it's going to do is going to say, okay, I'm going to give you something because you are lazy, right? And you're not working much. So I'm going to go down. Okay, I'm going to go down a little bit, right? I'm going to go down, but you are going to increase. But I'm going down. All right? And there is a moment where all three values are the same. And at that moment you have what is called a mechanism. So the thing fails. Okay? But now how do you do that? This moment becomes WU L squared over 16. This one right here, right? This moment is also WU L squared over 16. Why? Because always had to have that, right? So they had to be always that. And this one also becomes WU L squared over 16. So there's been a redistribution of the moments. Notice that this one reduced a little bit, this one increased something. All right? So now they all three are sharing pretty much the same amount. So when you tell me that your analysis shows this to be the moment, I can tell you are wrong. Your analysis should show you this one, right? But this is a plastic analysis, so this one is plastic, right? And this one is linear elastic. So it depends on the type of method that you're using, you will get different answers, right? But for this case, you have to design this to have that plasticity. It has plasticity meaning that it flows, right? That yielding there. So that's very important. Mm-hmm. Otherwise, it will not work. By mechanism, I mean that now this one is a plastic hinge, that one is a plastic hinge, this one is a plastic hinge. So now your beam then has a hinge, and a hinge. Well, three hinges will make a mechanism, right? It will simply break like this, right? Because now it has those three hinges. Right? So that's the maximum you can make it work. Right? But this is what sort of an idea of what is a redistribution. But your beam has to be designed for that purpose. That's why they increase in epsilon t to 0.0075, because we want more ductility in order to be able to reach these cases. Okay? And so that's one concept that you didn't learn, and now you know about redistribution. All right. So that's what it means by that. All right. Uh, unless you really need to find the smallest cross section for a given width, right? Your epsilon t that you select should be something between that 0.075 and 0.1. Okay? So right in there, that should be your value. Okay, so that's what we want. So that's what you want. You want to be there. Now you want the smallest cross section, you will use the epsilon t equals 0.003 plus epsilon ty. Why? Because that's the case that gives you what in terms of area of steel. The maximum area of steel that you can use. And the maximum area goes with your smallest cross section. Okay? So that's your maximum area of steel that you can use when you use this number. Okay? All right. So in general, then I can show you here, just to get you here to the figure that we've been using in the past, right? So you select the value from your tension control limit to the 0.0075. That's a good choice. Okay, that's okay. I mean, it works. Not bad. Right? But it would be much better if you pick a value from 0.0075 to 0.001. And you pick even more, that would be even better, more utility. Okay, so what's happening? Your area of steel is going down from a maximum to a minimum as you move to the right. So as you increase the epsilon t, you will need less and less amount of steel. And of course you cannot go below its minimum. Right? Okay. The more amount of steel you put, the less D you need to create a moment. And that means the smallest section. So as you go from the tension control to the minimum amount of steel, you are going from the smallest section to the largest section. So when do you get your largest section? When you use AS minimum. When do I get my smallest section? When I use the tension control limit for epsilon t, which is my AS maximum, right? So that's how this works. So tension control limit, maximum amount of steel, smallest section. AS minimum, largest section. Okay? So when you done that, see now it just shifted, I don't know how that shifted. Oh, that's about the table that we use, right? Oh yeah, these numbers. Okay. Next, what you're going to do is you're going to go to this equation here that we developed, right? In what, chapter 5? Yeah, chapter 5 we developed this equation. And so now on this equation, notice that you know your beta 1, you know the strength of the concrete you're using, you know your Fy, you know the concrete strain value, 0.03, right? And this is the value you're picking, your epsilon t, okay? So depending what you pick, you get a different value for rho, or in other words, you get a different value for the amount of steel. Of course, this value has to be greater than the rho minimum, otherwise you are not working well, right? So once you do that, the next step is to come in here and you make your mu less or equal than your formula for design strength. You're again replacing, as procedure A, you replace D minus A over 2 by 0.9D. But we're going to do one more replacement. The area of steel that now I know, right? I'm going to change it into a rho value. How? Well, the area of steel is the same as rho times B times D. So I'm going to replace this number into this equation, okay? So we're going to do that. And now we get something like this. Okay? And notice that here now, I know the phi factor because I'm going to assume it that is good, is in tension control, so it's 0.9. My raw value, that's the one I found here, right? My Fy I know. What I don't know are the dimensions, so I'm going to solve for these dimensions. But wait a minute, I got one equation, two unknowns. How do I going to do that? What you do is you set up a table, right? You assume a value for B and you solve for your D value. And you're going to get a table of different B's and different D's. Okay? And then looking at the table, you select the size you want. Okay? What are the things? So you got your B and you got your D, but you don't have your H. So how are you going to find your H? Well, now we do the other way around, right? We're going to add to the D 2.5, if we think about one layer. We're going to add 3.5 if we think it's two layers, right? And that will give us my H. Now, do not forget that the H is going to be a round number, unless you are doing joists, where you can, in that case, you can use 17.5 or 18.5 or 21.5, right? But in other cases, it's a whole number. So you get your D may be 17.3, you add 2.5, that gives me 19.8, it becomes a 20, okay? So you should always make a whole number for your H. Mm-hmm. The next thing is, okay, you got an H, but is that H good enough to satisfy deflections? So I need to make sure that the H is greater than the H minimum from the table from the ACI. Okay? That's your H minimum, not the value for design that we use 10 to 20% to make it bigger and so that way it will work. No, that's not that value. We're going to use the H minimum and compare. Once you've done that, you got your H, and so now you have dimensions, B and H. If I have dimensions, I can find my weight, and I compare that weight against the weight that I assumed right at the beginning, right? This is where you do the check of the weight. That's what it said. It's a guess. It doesn't matter. You just pick a value, all right? Now, if your weight that is new is greater than 10% of the old weight, okay, or your weight new is significantly less than your weight old, say 20%, 25% or more, then find new moments with the new dimensions and repeat these steps. Okay? Once you got to that point, now that you know your raw value and you have checked that your raw value works, right? This is your raw value. How do you find your area of steel? You multiply your raw times B times D. You get your area of steel. Then you go to the table, right? And you find the actual bars, right? And just in case you make a mistake someplace, recheck your AS minimum, make sure that it works. Finally, you repeat again the same thing as you've been doing in procedure A. You have to check for that your design strength is okay, is a valid design strength, and you can use it, and therefore these steps right here again are simply finding what? Phi times right? So you then make sure that that value is greater than your MU. Right? And then of course you have to sketch your cross section. Right? So all that, this is always the same. Okay, so let's use the procedure and see how it works. Okay? And so now we're going to go to the examples. I don't know why this is moving to all the pages. Somebody done something that it moves to all the pages. Okay. So we did that one, and then that one, and here it comes procedure B. So I think, Microsoft is not working anymore. Okay. There it comes, there it comes. He will come. Okay. Uh-oh. Come here. Oops. Okay, so here's the beginning of these examples. So let me see if I can erase this. Kind of slow. Okay. All right, so now example with procedure B. Here, different examples. 783, 789 pretty much is to help you understand the method, right? Then in 725, we're going to do this thing about the smallest, largest section. Remember, is maximum, is minimum, right? And 26 to 39 is when you have negative moments, okay? So that's what we are going to do. So first example then that you have here is this one where the designer reinforced concrete beam, simply supported, length is 30. The beam carries a uniform load of 1650. That notice that this problem is the one that we did in example 710, but I haven't preset the dimensions. Okay, so I approximate a beam weight, and as I said, you can use any value you want. In this case, 0.4. Right. Then I'm going to find my load combination, right? Including the weight of the beam that I found. There is the weight of the beam. So I do that, I get my moment, right? Next, I'm going to find my AS, and so I'm going to select an epsilon T 0075, and I'm going to put it in the formula for rho. So all the values we know, the only thing new that we're guessing is that epsilon T as 0.0075, and so that gives me now a rho value of 0.013.8. Is this value okay compared to the minimum? Okay. Since my F prime C is less than the 4444, right? So we check this formula for rho minimum, and that formula is 0.0033. Our value is higher than that, so we're good. We satisfy rho minimum. Next, I do the same as we did in procedure A. My MU has to be equal to my design strength. I'm going to replace the parentheses with a 0.9D. But in addition to that, I'm going to replace the area of steel with rho BD. And so my formula becomes this, where I know everything except the B's and the D's. And so when I solve this, I get this equation. Okay? That equation, I will come up and use a table, as I said. You assume a value of B, so you assume a B here, and you solve for D. You assume a B, you get a D. Assume a B, you get a D. Assume a B, you get a D. B, you get a D. Okay? All these combinations of B and D work with the assumed value of 0075. Okay? So whatever you pick, though, has to satisfy H minimum, though. Okay, so we don't want to do the calculation for deflections. Again, what pair will you use? Well, you are into, say, I want a very efficient structural shape. Remember, the ratio that you want to maintain is a 1.5 to 2. So, for example, I may want to pick something here, right? 14 and 21.2. Right? Notice that here you're getting into the 1-1 ratio. Right? Here you're getting into wider beam. It's more like a joist system. Right? So it depends on what you want. So in this case, I pick this one, 12. So I would get probably 24 as an H. So that's a ratio of 2. So let's see. B equals 12. D equals 22.8. I add my 2.5. It gives me 25.3. Remember, I need the whole number. So I went to 26. So my beam is 12 by 26. I'm going to check H minimum, right, from the table. So simply supported is L over 16. Span length is 30. Change it to inches. Divide by 16. So my minimum value is 22.5. I'm using 26. That's good. That's good, right? So let's go back here then. If I would have picked something like 17.7, right, then I probably will not be satisfying my H minimum. That means that if I decided to use that number, I have to do deflections. I have to calculate deflections. That's all it means. Yeah. All right. So now that I know the dimensions, it's 12 by 26, I can find the weight. The weight is 0.325. I mean, it's less than 0.4, but they're pretty close, right? And so probably we don't need correction, but just to show you how you do the corrections, well, you pick the new weight, right? And that's the new weight, and you correct your loads, right? And you find your new moment, and then you repeat the process. You repeat the process and solve for B's and D's. And notice there is not a big difference. Now we get 25. So you can use a beam of 25, but usually beams tend to be even numbers, but you can use 25. So 26, then again, so that way we don't have to do more changes. So 12 by 26. With that, I'm going to find my D value, but I don't know my bars. So I'm going to say that's about 2.5 less one layer. They give me 23.5. I multiply my rho that I found. Remember the rho that we got, right? Times B times D. That gives me the area of steel, 389. I go to my table of areas and I say, well, 381 is a little less than that, but I mean, it's close. It might work, right? And I already show you how to find this B, so I'm good. The actual D value is 2337. Now, why also, let me back up a little bit. So why I was able to use 381 versus 389? Because, right, because, and this is important, so let's mark it up here, see if it marks. Yeah. Because really I only need 25, but I'm using 26. So I'm using more depth than what I need, right? So that means I could have a little less area than what I need, right? Because I have enough age to compensate for that. So that's another reason why probably the 381 will work. And so we keep doing that and moving this. I mean, you want to check minimum, you can do it again just in case there was a mistake, but usually not. And finally, we're going to repeat this thing about the phi and sub n, right? We're going to find the A value. After the A value, we're going to check for my ductility. Notice that it came up pretty close to what I assumed. Sometimes it does, sometimes it doesn't. For grade 60, we know that the limit is 0.05. We satisfy that, so A is maximally satisfied. Phi factor should be 0.9. Okay. And then I go and find my design strength. I notice that I got 4,232,000, and I needed it. I needed what was my recalculated value right here. I need that. So 4,090. So I'm okay. So I satisfy that. Here is my design. So it's a 12 by 26 with 3 number 10s. And that is the same as example, as I said, example 710, right? And 710 was kind of the first example that we did using procedure A. Is it 17? No, maybe I need to change that. Let me see. No, I know. Okay, that's good that I went back to check this, because it looks like it's not example 710, it's this one, right? 716. Okay, that's a good point. All right, so 716. So 716, we have already 12 by 26, and we just did the design for that one, right? And notice that in the other case, by assuming our steel, we got about the same dimensions. But it's example 726, 716, so. Okay. So these here then, so this one then, the 710 has to be 716. Okay, so make sure you correct it in your notes. So we have a 716. So 716. Okay, so 716 is that example. All right, so it works. It matches these values, so we're good. Okay, not too much here. You see. So. Okay, now, so that one was 716. So this one, right? So that one, okay, so change this. Hmm. Okay. So this is really 716, right? And this one right here then should be 7617. Right? So that's the same example as 16, but remember we added the extra weight and it didn't pass, okay? Because it was too much weight and it didn't pass, even though we were getting the same dimensions. So the difference here is that with this method, you can actually come out with the right dimensions, okay? And so we move and we find a set of weights. So notice again, I mean, just guess the value, 0.04, that's good guess. We do the low combination, find my moment, it's the same. Now I need to assume an epsilon t. That means I'm finding my area of steel indirectly. So I get the same as before, 0.038, as we did in example in the 723 problem. Check minimums, create a table, right? By replacing what? The parentheses replaces by 0.9d, and the area of steel, right, is replaced by rho BD. And so that gives you that. Now that you got this set up, this is where you're solving. You assume a B, you get a D. Assume a B, you get a D. Assume a B, you get a D. Okay? Notice that for the same width, now we're getting a larger values for D. So this one picks up the effect of the load, right? So we're going to select the combination. In this case, I pick 14 and 27.5. I add 2.5, that's 30, 30 is a good number, so I keep it like that. I'm going to check my minimum. My minimum is 22.5. I'm using 30, so that's good. You always have to check the minimum. You don't want to check the fractions. I check my weight. My weight is a little bigger, but not much. But, I mean, I did here the recalculation so you know how it is done. So you find again your new W, your new moment, redo the table, and I get the same value, 30. So with that, I find my area of steel. I multiply times B. I don't know my D, so I have to assume it, right? 30 minus 2.5, one layer. I assume it, 531. With that, I go to my tables. I have 553, but that it will not fit because I only got 14. This one works, two number 11s with two number 10s in one layer. That works. Okay. Now in this case, I'm using, I'm assuming that D and D sub T are the same, but they're not really because you have different bars. But you just assume that. I mean, conservatively, to find your D, just assume the number 11 is being the centroid, so use number 11s as such, and that's kind of a good approximation. Okay? Your raw value then is 566 now, which is this number that you're selecting, divided by BD. So now notice that it got a little bigger, right? Which is good, but it will pass minimums. Okay? So we're okay. Finally, we're going to find the phi m sub n. So you find your A, find your epsilon t. Notice that the epsilon t got a little bit less than what we assumed, right? That's what they say. You may not get the same, right? So we got a little less. Right? And the reason is because we're putting more area than what we actually need, right? And so that makes difference. And so you can check it either by using the epsilon or using the C over D sub T, whatever you like. And that means that you're satisfying your 0.9, your A is maximum, you check your strength, and now the strength is okay, but you will need to use a beam that is 14 by 30 with two number 11s and two number 10s in one layer. Okay? So that is what this is about. This